Okay, now in this lesson, we're going to be integrating trigonometric functions. Now, in order to set up the rules for integrating such functions, we're going to use the derivative rules of these functions. So first, we're going to start with the fact that the derivative of sine x is cosine x. So since the derivative of sine x is cosine x, then an antiderivative of cosine would in fact be sine, because cosine is the derivative of cosine. So an antiderivative of cosine x dx would in fact be sine x plus k, of course k being the constant of integration here. Now, however, the derivative of cosine is in fact a negative sign. So if I were to find an antiderivative of sine x, in that case, I'd solve for sine x in the derivative rules. So by solving for sine x, that would give me that sine is the derivative of negative cosine x. Consequently, an antiderivative of sine x would be negative cosine x plus k. Now, the derivative of tan is secant squared x, or 1 plus tan squared x. We do know that secant squared is equivalent to 1 plus tan squared. Now, keep in mind that secant squared, now secant x is 1 over cosine x, so that could also be written as 1 over cosine squared x. So the derivative of tan is 1 over cosine squared, and 1 over cosine squared is equals to 1 plus cosine squared, 1 plus tan squared, sorry, and that's because of the Pythagorean identity. It could be justified easily using the Pythagorean identity. So consequently, whenever you're integrating 1 over cosine squared or 1 plus tan squared x, so the antiderivative in that case is tan x plus k. Now let's just move to the following examples here. Now over here for the first one, I need to integrate 2 sine 5 minus 3x. Now you notice that sine has a linear function. It's written in terms of a linear function. So whenever we have a function written in terms of a linear function, in that case, we'd actually think of using the compound formula for integration. So in order to use the compound formula, we'd need to actually refer to our table of integrals in order to actually find the rule that should be used here. So since the linear expression is inside sine, then according to the table of integrals, the integral of sine is negative cosine. So writing that aside, so the integral of sine x dx, that's the rule here. That's negative cosine x plus k. However, inside our integral, inside sine, instead of having an x, I have a 5 minus 3x. Now remember, this compound formula only works when the function is written in terms of a linear expression. So we have sine of 5 minus 3x. So instead of the x, we have 5 minus 3x. So our antiderivative would have a 5 minus 3x instead of the x, but we do not forget to divide by a, the slope of the linear expression, which in this case is negative 3. So this is the antiderivative of sine of 5 minus 3x. So if I were to go back to I, don't forget you originally had a 2 here, so it's negative 1 over negative 3, which is a 1/3 times 2, that's a 2/3 cosine of 5 minus 3x plus k, and that is our antiderivative. Now moving to the second one. Now the second one is in fact a secant squared. Now please keep in mind that a secant squared of x over 4 is in fact 1 over cosine squared of x over 4, and we know that 1 over cosine squared is a derivative of tan. So we know that 1 over cosine squared is the derivative of tan. These are all equivalent, these three expressions that we have here. So over here, again, using the compound formula. Now, I'm using the compound formula here because x over 4 is a linear expression. It is in the form ax plus b, where a is 1 over 4 and b is 0. So going back to the rule in our table of integrals, the integral of secant squared x dx is in fact tan x plus k. However, here instead of x, I do have an x over 4. So in our antiderivative, wherever we have x, we replace by x over 4, and we do not forget to divide by a. Now, a here is 1 over 4. So going back to our integral, now you do not forget that you had a half originally in the integral multiplying secant squared, so the half does multiply the integral of secant squared, and remember the process of taking a constant outside of the integral that only works with constants. It doesn't work with a variable. So over here, 1 over 4 is a 4. A 4 times half, that's a 2. Tan of x over 4 plus k. So that is our second antiderivative. Now, moving here to our third antiderivative. Now, you notice I also have a cosine function. However, inside cosine, I have a quadratic function. I do not have a linear function, therefore the compound formula does not work. However, you notice that you have inside the integral, you'd have an x multiplying cosine. So usually in these cases, we do check for the substitution method in case it works or not. And for the substitution method to actually works, whatever you set as a u, you need its derivative present inside of the integral. Now you need to refer to our previous lesson on the substitution method with basic functions in order to make sense of it. So over here, I'd notice that the expression inside cosine is x squared plus 3. Now, if I set u to be x squared plus 3, if I consider this in the form of cosine of u. Now, in order for the substitution method to work, I must have the derivative of u present in the integral. So let's just check for the derivative of u. Now, we know that du is 2x times dx. Now the derivative of x squared is 2x, and the derivative of 3 is 0 because that's a constant. So, and please remember the notation with the differential. I'll remind you that whenever you have u prime is in fact du over dx by Newton's method. So cross multiplying would leave you with du equals to u prime times dx. So that is the differential of the new variable you're introducing. So do not forget to have the derivative of u multiplied by dx because of the Newton's notation. So, okay, so let's just look at our integral. Now, over here, we know that the derivative of x squared plus 3 is 2x. By looking at the integral, we notice that we have an x times dx. We do not have a 2x times dx. Now, when the difference is just a constant, that's okay, because remember, we can always divide both sides by 2, leading to half du equals to x times dx. Now I have x times dx written in terms of a constant times du. Remember that this process cannot be done with a variable. You cannot divide both sides by a variable in order to reach the expression inside the integral. So that only works if they are only differing by constant. So over here, going back to our integral and doing the proper substitution, x squared plus 3 is u, and x times dx is half du. So which leaves me with our integral being equals to, and now don't forget that half goes outside of the integral, and then we'd end up with the integral of cosine u times du. Okay, so now half would actually multiply the antiderivative of cosine u. So cosine u, its integral would in fact be sine of u plus k, our constant of integration. Now, bringing back the expression of u in terms of x, that would give me my integral to be equals to half sine of x squared plus 3 plus k. So that is our integral. So if we just recall a bit, we've just seen a couple of examples here where we actually integrated trigonometric functions using the compound formula based on our integration rules here. And remember that the compound formula is a particular case of the substitution method. Now, over here, where the compound formula did not work, we were able to integrate here using the substitution method. And remember, the substitution method basically works whenever the expression you set as u, you'd have its derivative present in the integral multiplying dx. That's the only case where the substitution method would actually work. Now, we could also be integrating trigonometric functions using trigonometric identities. So over here, we'd notice that I have 2 cosine squared 3x minus 1. The fact that cosine is squared would not in fact allow me to use the compound formula or the substitution method. So over here, I need to think of another method. Now, if we look at the integrand, which is the expression inside the integral. Now, if we look over here at 2 cosine squared 3x minus 1, now it does remind me of a specific identity. The identity which is in the form 2 cosine squared a minus 1. And we do know that 2 cosine squared a minus 1 is in fact cosine 2a. However, what is a here in this case? Now it's good to also go back and recall the trigonometric identities, the double angle formulas of sine and cosine. Now over here, if we compare with the integrand, with the function inside the integral, we'd notice that a here is 3x. So 2a would in fact be 6x, so which leads me to my integral as the integral of cosine 6x dx. Now over here I have it in the form cosine of u, where u is linear, so I could use the compound formula. So over here, by referring to our table of integrals, we know that cosine u, an integral of cosine u, would in fact be sine u plus k, and over here u is 6x, so over here that would in fact be 6x, and we do not forget to divide by a, which is the derivative of the expression inside. Now I used u here, I could have used x, it's the same thing, it doesn't really matter as long as the variable I've used fits the one in the differential. So over here we do not forget to divide by a, which is the slope of the linear expression. So which leaves me with my integral being equals to 1 over 6 sine of 6x plus k, and that is our integral. Now, in the following lesson, we're going to be integrating trigonometric functions using the method of linearization. So we're going to be taking it a step further than this, as the method of linearization in fact uses the compound identities of the trigonometric functions, or what could also be called the addition formulas.